Welcome back. In today's episode, we'll build on what we explored in our previous discussions, specifically our deep dive into the MLE bench. If you remember, we talked about how the MLE bench provides a framework for evaluating machine learning agents on practical tasks. And today, we'll explore how a new model, the Diff Transformer, might fit into that.
Yeah, I remember the focus on real-world ML tasks in MLE bench, like data preprocessing and model training. How does that connect to the Diff Transformer?
Great question. The Diff Transformer, like the models we discussed earlier, could be evaluated using similar benchmarks from MLE bench. This model introduces a fascinating mechanism to handle attention noise, which could make it more effective in machine learning tasks requiring in-context learning or key information retrieval. You could imagine testing it against those same Kaggle leaderboards we mentioned before.
So, we're comparing this new architecture to the ones we've already seen, right? Does it outperform previous transformer models in those areas?
Compared to traditional transformers, Diff Transformer is more efficient and scalable. It uses fewer parameters, which reduces computational costs, and it's better at managing longer sequences of data, which is perfect for tasks like summarization or document analysis. The model even mitigates hallucinations, an issue we've often seen with large language models.
Sounds like it's making big strides in efficiency. What exactly will we be covering about this model today?
We'll be discussing how Diff Transformer's differential attention mechanism works, and how it improves the model's focus on relevant information. We'll also look at its architecture, how it compares with other models, and dive into some evaluation metrics to see just how much better it performs in tasks like key information retrieval, scalability, and language modeling.
I'm really interested in how it manages to handle those long context tasks better than the standard transformer models.
Exactly, that's one of its key strengths. It scales well with data size and model parameters, making it adaptable for real-world applications, just like we saw in MLE bench. So let's bridge over to the details, starting with the core innovation, the differential attention mechanism and why it makes such a difference. Ready to jump in?
Absolutely. Let's get into it.
All right, let's begin with an overview of the abstract. This paper introduces something called the Diff Transformer, which is a variation of the standard transformer model. The problem they address is that regular transformers tend to pay too much attention to irrelevant information, which they refer to as attention noise. Their approach, the Diff Transformer, focuses more on the important context by amplifying relevant attention and canceling out the unnecessary parts. The key innovation here is the differential attention mechanism, which compares two different softmax attention maps and then subtracts one from the other to eliminate noise.
So, if I understand correctly, the Diff Transformer tries to be more selective about what information it pays attention to. By subtracting the two attention maps, it can filter out irrelevant details and highlight the key information. Is that right?
Exactly, you got it. This mechanism works like noise-canceling headphones. The noise, in this case, is unnecessary attention that the model might otherwise spend on irrelevant parts of the context. By subtracting the two maps, Diff Transformer reduces this noise and helps the model focus better on what's important.
That makes sense. So, what kind of improvements does this bring to the transformer model?
Good question. They tested Diff Transformer in several areas and found that it improves performance in various tasks, particularly in language modeling. It handles larger models and more data more efficiently. They also found it to be especially helpful for long context tasks like summarization and question answering. Not only does it focus better on key information, but it also helps with reducing hallucinations, which is when a model gives incorrect or made-up responses due to focusing on the wrong details.
Interesting. And it works with things like long documents too, right? Since you mentioned long context tasks.
Yes, exactly. Diff Transformer shines in cases where a model needs to handle a lot of context. Traditional transformers can get overwhelmed by the amount of information in long documents, but Diff Transformer keeps its focus better. It's also more robust when it comes to learning from context in different orders, which has been a challenge for regular transformers.
So, Diff Transformer is not only more accurate, but also more flexible in how it learns from context. That seems like a big improvement.
That's right. It's both more accurate and more resilient to issues that affect regular transformers. The authors even mention that it could be a great foundation for building larger models because it scales well with size and data. In summary, the diff transformer helps solve a key problem in attention mechanisms, namely focusing too much on irrelevant information. By introducing the differential attention mechanism, it improves the model's efficiency and accuracy, particularly in tasks requiring long context understanding. Now that we've wrapped up the abstract, let's dive into the introduction of the diff transformer. The authors start by talking about how transformers, particularly the decoder-only models, have become the go-to architecture for large language models. The attention mechanism is central to the transformer's ability to weigh the importance of tokens in a sequence. However, there's a big issue. Transformers often over-allocate attention to irrelevant details, or what they call attention noise.
So the problem is that transformers can get distracted by unimportant information, which reduces their accuracy.
Yes, exactly. Transformers distribute their attention across all tokens in a sequence, which sometimes means focusing too much on irrelevant parts. This attention noise can drown out the correct answer or the important details.
I see. And how does the diff transformer address that problem?
The diff transformer introduces something called a differential attention mechanism. The core idea is that it calculates two separate softmax attention maps and subtracts one from the other. This subtraction helps cancel out the noise. Think of it like noise-canceling headphones. By comparing two signals, the noise gets filtered out, leaving only the relevant attention scores.
So instead of just accepting all the attention it calculates, the diff transformer is more selective by eliminating unnecessary attention. That seems like a clever approach.
Exactly. And the authors even show, through visualizations and experiments, how the diff transformer pays significantly more attention to the correct answer compared to a standard transformer. It helps boost the model's ability to retrieve key information from long and complex contexts.
That makes a lot of sense. Does this improvement only apply to specific tasks, or is it a general enhancement across different types of models?
Good question. It's actually a general improvement. The diff transformer improves performance across various tasks, but it particularly excels in tasks where context is crucial, such as language modeling, key information retrieval, and in-context learning. It's not only more accurate, but also scales better as the model size and data increase. To sum up this part, the diff transformer tackles the issue of attention noise by introducing a differential attention mechanism. This makes it a more efficient and focused model, especially in handling large contexts and long sequences. All right, moving forward from the introduction, let's now explore one of the core ideas behind the diff transformer, which is the differential attention mechanism. In standard transformer models, attention noise is a big challenge. This noise happens when the model focuses too much on unimportant parts of the input. But with the differential attention approach, the goal is to cancel out this noise.
So, this is where the diff transformer starts becoming more efficient? It handles attention noise better?
Exactly. In differential attention, the model uses two separate attention heads to compute attention scores. These are calculated from two softmax attention maps. Then, the real trick happens. One attention map is subtracted from the other. By doing this, the diff transformer essentially filters out irrelevant attention, allowing it to focus on what's truly important in the context.
That subtraction idea sounds clever. So, it's like comparing two different perspectives on the same input and then using the difference to reduce the noise?
Yes, that's a great way to think about it. It's similar to how noise-canceling headphones work. They capture both the external sound and its opposite to cancel each other out. Here, the two softmax maps capture different aspects of attention, and subtracting them results in clearer, more focused attention on the important elements.
And this approach helps the model improve performance in language tasks, right? It seems like a small tweak, but I'm guessing the impact is quite significant.
Exactly. The differential attention mechanism results in much better performance for the model, particularly in long context tasks like summarization and question answering. The subtraction of the two attention maps reduces unnecessary distractions, allowing the diff transformer to retrieve key information more effectively. This also helps the model reduce hallucinations, situations where the model gives inaccurate or made-up responses because it overattended to irrelevant parts of the context.
I get it now. So it's all about improving focus, cutting out the extra noise, and making the model more accurate in its responses.
That's right. This small but powerful mechanism has a big impact. It enhances attention by canceling out the irrelevant details, which is critical when the model deals with large volumes of information. It also makes the diff transformer more scalable and efficient as the model size grows, which is a key advantage for large language models. Now that we've discussed differential attention, let's look at how this mechanism fits into the overall architecture of the diff transformer. The architecture is quite similar to a standard transformer, but with a few notable differences. The model is stacked with multiple layers, and each layer consists of two main components: a multi-head differential attention module and a feed-forward network module. The differential attention mechanism is at the heart of this, replacing the standard softmax attention used in conventional transformers.
So even though it has a new attention mechanism, the rest of the architecture is still similar to the classic transformer setup, right?
Exactly. The overall layout remains familiar, but the differential attention module is what makes it unique. It's designed to amplify the focus on important details while reducing the attention noise. Each layer normalizes the input, applies the differential attention, and then passes the result to the feed-forward network. This is followed by another normalization step, ensuring stability throughout the network's training.
And I assume the multi-head attention is still used, right? But in this case, it's modified with the differential attention approach?
Yes, the multi-head mechanism is still there, but it's adjusted to work with differential attention. Multiple attention heads allow the model to focus on different aspects of the input simultaneously, but now it filters out irrelevant information even more efficiently. After the attention is processed, the outputs from each head are concatenated and normalized, just like in a standard transformer.
That makes sense. So it combines the flexibility of multi-head attention with the noise-canceling power of differential attention. Sounds like a strong architecture.
You've got it. And this architecture also scales well with model size and the amount of data used. The authors mention that it can handle very large contexts effectively, which makes it useful for tasks involving long documents or complex sequences. Now that we've gone over the diff transformer's architecture, let's shift our focus to its performance in specific tasks. First up is language modeling. In this section, the authors evaluated diff transformer against other transformer-based models on a wide variety of tasks, and it performed quite well.
How well did it perform in comparison to other language models? Is it noticeably better?
Yes, diff transformer consistently outperforms well-trained models like OpenLLaMAV2 and StableLM across many tasks. It's especially good at zero-shot language modeling. The paper reports that diff transformer achieved better accuracy across various tasks without needing fine-tuning or additional training data, which shows its robustness.
So, diff transformer doesn't just match other models, but actually exceeds them in terms of performance on diverse tasks. That's pretty impressive.
Exactly. And it's not just about accuracy. In the section on scalability, the authors also mention that diff transformer achieves the same performance as a larger transformer model, but with fewer parameters and training tokens. For instance, a 6.8 billion parameter diff transformer matched the performance of an 11 billion parameter transformer. This shows that diff transformer is more efficient in terms of both size and data consumption.
That's a big difference in scale. Being able to use fewer resources but still match or outperform larger models is a huge advantage.
It is. This efficiency is one of the standout features of diff transformer. The paper also highlights the model's ability to handle longer contexts effectively, which is another big challenge for standard transformers. In long context evaluations, diff transformer showed significant improvements over regular transformers. It can handle context lengths up to 64K tokens and still maintain high accuracy, which is critical for tasks like summarization or processing lengthy documents.
Handling longer context better must be really important for tasks that involve lots of data or long documents. Does it do the same with key information retrieval?
Yes, exactly. In key information retrieval tasks, Diff Transformer showed a marked improvement. The authors tested it using the needle in a haystack task, which evaluates how well the model can retrieve specific, critical information from a large and noisy dataset. Diff Transformer performed significantly better than the standard transformer, especially when multiple needles were embedded in long sequences. This proves that Diff Transformer isn't just about understanding long contexts, but also about retrieving essential details more accurately.
It seems like Diff Transformer really excels in both handling long contexts and efficiently retrieving key information, all while using fewer resources. That's a major upgrade over standard models.
Absolutely. These improvements make Diff Transformer highly effective in practical applications where large volumes of data and key information retrieval are crucial, all while maintaining efficiency in model size and data usage. All right, let's move on to the next section, where the authors evaluate the Diff Transformer's capabilities in some specific areas like in-context learning, contextual hallucination, activation outliers, and ablation studies. First, in-context learning. The authors highlight how Diff Transformer outperforms the standard transformer in terms of accuracy and robustness during many shot classification tasks. This is important because it shows how well a model can learn and adapt from examples provided in the input context.
Right. So it's about how well the model can learn directly from the input, instead of needing more training or fine-tuning.
Exactly. In particular, Diff Transformer demonstrates much higher accuracy when more examples are given. It can handle increasing numbers of samples while maintaining consistent performance. The robustness of Diff Transformer also stands out here because its accuracy doesn't drop much when the order of examples is changed, which has been a weak spot for regular transformers.
I see. So not only does Diff Transformer perform better in context learning, but it's also less sensitive to the order of the examples. That's a big advantage.
Yes, and that brings us to the next part. Contextual hallucination. This is a common issue with language models where they might generate inaccurate or made-up information, especially when dealing with complex contexts. Transformer addresses this problem effectively, reducing hallucinations in both text summarization and question-answering tasks. For instance, when evaluated on datasets like CNN/DM and HotpotQA, Diff Transformer showed significantly fewer hallucinations compared to the standard transformer.
So it's much better at sticking to the facts, especially in tasks that require summarizing or answering questions based on context.
Exactly, and this aligns with its improved focus on key information. Now, onto the analysis of activation outliers. These are large spikes in the model's activations that can cause issues with training and inference, especially when it comes to quantization. Spartzes. Diff Transformer reduces the occurrence of these outliers, which could make it more efficient and stable when scaled to larger models or when applied in environments where lower precision computation is necessary.
That sounds like a really useful improvement, especially for making the model more scalable and efficient. What about the ablation studies?
Great question. The ablation studies help to isolate the specific contributions of different components of Diff Transformer. For instance, they tested the effect of removing certain elements like group norm, and the results confirmed that the differential attention mechanism is the key driver of the model's improvements, rather than other architectural tweaks. So, the core innovation differential attention is what's really making the difference in terms of performance gains. All right, now we've covered the key technical details and evaluations. To wrap things up, the conclusion of this paper provides a clear summary of the Diff Transformer's contributions. The authors introduced this model as a solution to the challenge of attention noise, which is a major issue in standard transformers. Transformer offers a unique differential attention mechanism, which amplifies relevant attention while canceling out the noise, leading to improved model performance.
So the main takeaway is that the differential attention mechanism really improves the model's ability to focus on important information, right?
Exactly. The model showed superior performance in several key areas like language modeling, long context handling, and key information retrieval. It also demonstrated notable improvements in context learning and reducing hallucinations, especially in tasks like summarization and question answering. These advancements make the Diff transformer a strong candidate for large-scale language models moving forward.
It seems like this could have a big impact on future models, especially since it performs well while using fewer resources and reducing errors like hallucinations.
Yes, that's a crucial part. Another interesting point is that the differential attention mechanism can easily integrate with other attention optimization methods like flash attention, making it a very flexible model for future developments. Overall, Diff Transformer stands out as an efficient, scalable, and accurate architecture that addresses some of the core challenges faced by traditional transformers. All right, that wraps up our discussion on the Diff Transformer. We covered a lot today, starting from its differential attention mechanism, how it handles long context tasks better than traditional models, and its efficiency and resource usage compared to standard transformers.
Yeah, and I think it was really interesting to see how it also reduces hallucinations and improves key information retrieval. Definitely a model that could be a game changer for handling large-scale data.
Absolutely. It's a promising direction for future developments in machine learning. And of course, it ties back nicely to what we've discussed in previous episodes about evaluating models on practical tasks.
Agreed. Definitely some points here we can revisit in future discussions, especially as more benchmarks and real-world applications come out for the Diff transformer.
For sure. Thanks to everyone for tuning in today, and we hope you found the conversation insightful.
Yeah, thanks for listening. Looking forward to our next episode.